Okay, another energy cycle. This one's going to involve ionic compounds. First thing to review is what is a lattice enthalpy? A lattice enthalpy is the enthalpy change required to convert 1 mole of an ionic compound into gaseous ions. Represented with sodium chloride as the example. That would be starting off with 1 mole of sodium chloride solid, so solid table salt, and it would be the energy change or the enthalpy change required to convert that into gaseous ions. So taking this solid ionic compound and actually separating it apart into not just an aqueous solution, but actual ions in the gas phase. So you could probably guess that because you are not only going from solid to gas, you're separating ionic ions that are quite highly charged. This is going to be very endothermic. Okay, so you're separating ions. Anytime that we separate attractions, that's going to require an energy input. And so this is a very endothermic process. So remember that separating attractions is endo. When attractions come together, that's exo. So what factors increase lattice enthalpies? Well, anything that increases charge density will increase a lattice enthalpy. So basically you got two ways you can do that. Probably the most important is the increasing charge of the ion. So 2+ ions have greater lattice enthalpies than +1 ions. And same thing goes for minus ions. -2 ions have greater lattice enthalpies than -1 ions. And it would be the same for going to +3, +4. So higher charges, if you're asked to predict between a couple of different compounds, you'd predict that the ones with the higher charges have higher lattice enthalpies because higher charges have higher attractions, and it will therefore take more energy to break them apart. The second factor, probably the less important factor, so we'll number them 1, and then the second thing to consider would be number 2. When things have the same charge, you would want to compare their ionic radius. So, and decreasing ionic radius will make a stronger lattice enthalpy or higher lattice enthalpy, because if the same amount of charge is spread over a smaller ion, it's more concentrated and the attraction will be stronger. So this is sort of harking way back to the periodic table, and you're thinking about number of PELs, principal energy levels. So 1 principal energy level will have a greater lattice enthalpy than 2, will have a greater lattice enthalpy than 3 principal energy levels. Okay. So in terms of examples, in terms of the increasing charge one, this would be like comparing magnesium chloride to sodium chloride. And because magnesium is a 2+ ion and sodium is a 1+ ion, and the chloride in both examples is the same, we would expect this one to have a higher lattice enthalpy because the magnesium has a greater charge. For this one, it would be like comparing lithium chloride to sodium chloride. Lithium is only has 2 principal energy levels, and let me pull this out of the way. Whereas the sodium has 3 principal energy levels, so they're both 1+ ions, but since lithium is smaller, we'd therefore expect the charge to be more concentrated, and it would take more energy to pull apart lithium chloride than sodium chloride. So you'd be expected to predict those trends on paper 1. On paper 2, you can use the data booklet. Table 18 has lattice enthalpies, and this first table has them for singly charged, so +1s and -1 ions. And you can essentially see that trend. As we go down the table, you're getting bigger and bigger ions, more and more principal energy levels, but with the same charge. And you can see that as the ions get bigger, the lattice enthalpies go down. So this would be lithium fluoride versus sodium fluoride versus potassium fluoride, and so on. Same exact idea here. As you go to the right, the ion is getting larger. We're going down the periodic table, and you can see the lattice enthalpy shrinking. Down here in these other tables, you have ions with greater charges, so things like calcium, beryllium, magnesium, those all have +2 charges. And then in here, you've got some transition metals like copper and silver to deal with and talk about. So these are ones that they might reference on the IB exam. Okay, the next enthalpy that we're going to worry about for these this new energy cycle is called an enthalpy of hydration. This is the enthalpy change when 1 mole of gaseous ions are completely mixed with water. So if you represent it as a chemical equation, it would be these ions turning into, superscript those, these ions turning into aqueous ions starting as gaseous ions. Okay, well, this is essentially the formation of attractions. So it's going to be exothermic always. You've got something that's a lone gaseous ion, and now you've got all this water that's going to attract to it and stick to it and form attractions with it. And you can see these are pictures on the right represent hydrated ions. And so there are these attractions that have formed between the water and the ions. That attraction has a special name, which I think we talked about during bonding, but just to review it, it should be called an ion-dipole interaction. Okay? So it's a special kind of attraction that forms between an ion and the polarity of a molecule, the dipole of a polar molecule. So this ion-dipole interaction is formed, and that means that we're going to be exothermic. For enthalpies of hydration will always be exothermic. Okay? And what increases the magnitude of enthalpies of hydration? The exact same thing that increases the magnitude of lattice enthalpies, charge density. Okay? I don't know why that just went back to this old font, but let's fix that. Okay, charge density. So it's the same thing, increasing charge and decreasing ionic radius. Okay. I'm not going to bother with the examples. You can see it right here in the table. So again, you'd be expected to know this for paper 1 and be able to predict which would have a higher enthalpy of hydration or how to represent it in a chemical equation. But if you look at it here, for cations, again, you're getting larger and larger as I go down from lithium down to cesium, and you can see that that lattice enthalpy of hydration is decreasing in magnitude. Same thing goes here. For the 1- ions, as they get bigger, the values get smaller. As the charge goes up, you can see there's a really significant jump in how big the enthalpy of hydration is, again, jumping up to +3, and it gets even larger. They've also included some polyatomic ions, which would be harder to predict what the lattice enthalpies would, the trend would be, but same basic rule applies that these 1- ones tend to have smaller lattice enthalpies of hydration than the 2- and smaller still than the 3-. And the last enthalpy change to be concerned about for these energy cycles is called the enthalpy of aqueous solution. So the enthalpy change when 1 mole of an ionic compound is dissolved in water. So this is what you would have experienced in daily life, which would be taking salt and dissolving it in water, and whether or not that enthalpy change is going to be exo or endothermic. So again, this is another table in the data booklet, table 19, and it's got a bunch of common ionic compounds that get listed, and it's listing their enthalpy changes. So you can see here that sometimes they are endothermic and sometimes they are exothermic. Okay? Whereas the previous ones, the lattice enthalpy is always going to be listed as endothermic values, and the enthalpies of hydration are always listed as exothermic values. And so this is the one that can vary. Okay, so how do these fit together into an energy cycle? You may have already kind of spotted it as I talked about it. Essentially, if you take an ionic compound here and you dissolve it in water, you're going to end up with hydrated ions. And that's the enthalpy of aqueous solution. Here it's written as the heat of solution, but we're going to call that the enthalpy of aqueous solution. That's this change here. Okay, so just taking salt and dissolving it in water. Now, it should add up to the same value, according to Hess's law, if we first vaporize the ions into gaseous ions. That's the lattice enthalpy. And then if we allow those gaseous ions to come together and with water and become aqueous ions, which is called the enthalpy of hydration, those two changes should add up to this original enthalpy of aqueous solution. Okay? Solved with simultaneous equations, we see the same thing. We've got the solid going to gas. This first is the lattice enthalpy. If I then look at the enthalpies of hydration, which are the gaseous ions becoming the aqueous ions, if I add those all together, then I see that the gaseous ions cancel out and the solid ends up becoming aqueous. So if you add together the lattice enthalpy with the two enthalpies of hydration that you care about, it should add up to the enthalpy of aqueous solution. So will it be endo or exothermic to dissolve a salt? Well, that depends. It depends on how these values compare. If the lattice enthalpy is smaller than the combined enthalpies of hydration, you'll get an exothermic enthalpy of aqueous solution. So when it's exothermic, the enthalpies of hydration are larger in magnitude than the lattice enthalpy. It's all about magnitude, because the lattice enthalpy is going to be listed as a positive value. It's just how it's defined. Enthalpies of hydration are listed as negative values. So we care about the magnitude here. You can see in this diagram it says negative lattice enthalpy, and that's when the arrow points up. That makes it the, well, actually for us, I see that that's false. Our lattice enthalpies are defined as, in the IB, they're always going to be defined as positive values. So I'm going to erase this little negative sign. Okay, and I'm going to erase it down here too. Okay, and then so clearly the reverse is also possible. We're going to have endothermic enthalpies of solution, aqueous solution, when the lattice enthalpies are greater than the enthalpies of hydration. So sometimes dissolving a salt absorbs energy from the water and it gets really cold, and that would be because it takes more energy to break apart the ionic compound than you get back when the ions mix with water, and so you get a positive enthalpy of solution. So both are possible. Some salts are extremely exothermic in water and some are extremely endothermic. This is actually how some cold and hot packs work. All that they have inside them is a little pouch of water and a little pouch of salt. And when you pop it, you are mixing the salt and the water, and it can either get extremely cold or it can get extremely hot, and you can use that to deal with whatever problem you've got going on in your muscles. So as a summary of this energy cycle, what do you need to know? You need to know how to represent lattice enthalpies, enthalpies of hydration, and enthalpies of aqueous solution with chemical equations. Those we did on the first 3 slides. You should know the factors that increase lattice enthalpies and enthalpies of hydration. Those are charge density, so essentially either increasing the charge on the ion or decreasing the size of the ion. The energy cycle is fairly simple. Lattice enthalpies plus enthalpies of hydration add up to the enthalpy of aqueous solution. And overall, the relative size of lattice enthalpy in terms of its magnitude compared to the magnitude of the combined enthalpies of hydration of the ions involved determines whether or not dissolving an ionic compound is exo or endothermic. Last final note, let me zoom down here. Okay, so in some cases the process is so endothermic, the enthalpy of aqueous solution it's so endothermic that the process is too unfavorable to happen. And so this can be an explanation for why some salts are pretty much insoluble in water. Some things just won't dissolve. And if the ions find each other, they form precipitates in those double replacement reactions we may have done a long time ago. When this happens, it's because the enthalpy of solution is so endothermic that it's not energetically favorable to happen. There's not enough energy to make it happen, and so the ionic compound actually won't get pulled apart by water. But that is this one other example of an energy cycle.